Welcome everyone. I'm Dave Tilbrook from the Department of Fundamental and Theoretical Physics here at ANU, and this is the second seminar in the AIP Theoretical Physics seminar series for this year, 2023. I'd like to start by acknowledging the people of the Ngunnawal Nation, the traditional custodians of the lands upon which ANU is located, and of course we acknowledge the traditional custodians of lands all around Australia. Our previous seminar, which was held a couple of weeks ago, was given by Dr. Fiona Shanahan from the Centre for Theoretical Physics at MIT, who talked about machine learning and artificial intelligence for calculations in lattice quantum field theory. It was a good talk, and if you missed it and you'd like to see it, it's available on the AIP YouTube channel, as this talk will be also within a few days. So today's speaker is distinguished Professor Peter Drummond from Swinburne University of Technology in Melbourne, where he is the Research Centre Director of the Centre for Quantum and Optical Science. I hope I got that right, Peter.
Actually, that's out of date.
Oh, it's out of date.
We have a new centre for
I knew I was right to check.
Professor Reid is a director.
Okay. Well,
we've changed the situation.
So what's the new centre called?
It's the Centre for Quantum Science and Technology Theory.
Oh, okay. Even better. It's got the word theory in the title. I like it.
And it's directed by Professor Margaret Reid.
Oh, okay, good. All right.
Yeah.
So Peter has had a long and distinguished career in physics, as we all know, and continues to make really significant contributions to Australian physics. His physics education was at the University of Auckland and Waikato University in New Zealand and at Harvard University in the States. He's also worked at Auckland and Queensland University, Rochester University, the IBM research laboratories in the US and the NTT basic research labs in Japan, to name just a few. And of course, given his stature, he's been invited to attend and to be a visiting professor at universities all around the world before taking up his position at Swinburne. And as you heard, the director of a new centre there. He is the author of over 260 research papers, ranging from fundamental tests of quantum mechanics and soliton physics to stochastic equations of quantum fields and so forth. Specifically in relation to that, he developed with Professor Crispin Gardner the positive P phase-space representation, which was a generalization of the Glauber-Sudarshan P representation, I think. Is that right, Peter?
That's correct.
Yeah, which found extensive applications to the wide range of problems in experimental physics, but and theoretical physics. But I don't know whether Peter's going to mention this during this talk, but I thought I would mention that, which is on a slightly different topic, but I believe the positive P phase-space representation is really interesting, not just for its original applications, but also just from a theoretical point of view. Within the context of the mathematical formulations of quantum mechanics. So if you're interested in mathematical formulations of quantum mechanics and alternative mathematical representations, I really suggest that is worth making a study of. So that brings us to today's talk, which, as you would have seen from Peter's abstract, relates to quantum computing, and particularly to the validation of important potential quantum algorithms, or just in general, if quantum computing is going to work in the way that we expect. Amongst other topics, Peter's going to address, I believe, an apparent conflict between some recent experimental data and theory and any potential implications for claims of computational advantage. His talk today is entitled Validating Quantum Computers, Are They Correct? Thanks, Peter. Over to you.
Well, I'd like to start by thanking the organisers for inviting me to give this presentation. And I just want to make sure that people can actually hear me. Is the sound coming through clearly?
It's coming through for us. Yeah.
Okay. So yes, the talk today will be about validating quantum computers, which is not something that people normally seem to worry about very much, because there's a kind of assumption that people have made, since digital computers are usually very reliable, that quantum computers, of course, will just perform as you would expect them to perform in an ideal world. But the problem is we don't have an ideal world, and we have to actually check that computers work. So just to try to give you a little background, I don't know how many people have studied the background of digital computers, but there was a period of time when even Intel Corporation was producing floating point chips that just didn't work. They gave wrong answers, which cost the corporation billions of dollars before they could correct it. So just simply to make sure a computer is working correctly is a very important problem. And I'd like to thank my co-authors, Alex Dellios, Margaret Reid, Bogdan Opanchuk, Manasham Tanabadu, and Ned Goodman for some of the contributions they've made to this work. So I'll start by talking about the concept of quantum computational advantage, which has been a very major news item in physics in recent years, over the last 2 or 3 years especially. One particular method of displaying this is Gaussian boson sampling. I'll talk about how phase space mappings can allow you to verify whether experimental data is correct. I'll compare theory versus experiment in the largest recent computational experiments, and then give some kind of what you might call an outlook for how you would try to extend these methods to future networks. Okay, so just to start, we have this concept of quantum computational advantage, which has been in the news recently and has resulted in a lot of corporate interest as well. So currently, Google Corporation in the USA has a machine which has claimed quantum advantage with 53 qubits, although this is somewhat disputed by IBM Corporation, who claim that they could do a simulation of that in a reasonably short time. So perhaps the advantage is not sufficient from their perspective. USTC in China has claimed a 100 qubit quantum advantage experiment. That in turn was disputed by Google Corporation. So you can see all these companies tend to argue with each other. They then produced a 144 qubit machine and reported that in 2021. And then in 2022, last year, Xanadu Corporation of Canada combined with NIST in the USA to demonstrate a 216 qubit Gaussian boson sampler. Now, as a general comment on this, IBM scientists have claimed that any claim of quantum advantage would require full-scale error correction. So in a sense, I would say that indicates they're a little skeptical about some of these claims, but I won't go into what they think is necessary. Another option that's been in the news recently is the NTT Corporation coherent icing machine, which is a much more useful machine than some of the earlier ones because it's claimed to solve useful optimization problems, that is, genuine hard problems with many applications. Although they have 100,000 qubits, really it's thought that it's mostly a classical machine at the moment. So in general, we do need to carefully theoretically analyze all these systems to understand what's going on. The source of quantum advantage doesn't seem to be in dispute. The main difference between quantum and classical systems is you have quantum superpositions and entanglement. Certainly gate-based quantum computers require superpositions. Shor's algorithm requires superpositions. We don't have any classical methods known for large factorizations. And Gaussian boson sampling, which is another technology I'll talk about, that also can't be explained without quantum superpositions. So it seems very clear that that's a necessary ingredient for quantum advantage in computing. So then the three main kinds of computer that have been proposed to have quantum advantage are the coherent icing machine, which, as I said, is a large-scale optimization machine, but it's not clear how quantum the advantage is in their case. Then there's the Google Corporation random circuit generator, which is a gate-based machine. And finally, what I'll be focusing on in this talk, the Gaussian boson sampler, with the two biggest examples from China and the US. Okay, so the reason why I, as a theorist, like the Gaussian boson sampler is because it's really simple to understand theoretically. Its purpose is simply to generate a type of random number. But these outputs that it generates are exponentially hard to generate classically. Now, the problem is that I'll talk about today, are these machines actually giving the correct results? And this is not so trivial because it's not as easy to check a random number distribution as it is to check that you've got two numbers that are factors. If you have two numbers that are factors of a large number, you multiply them together and you can tell immediately, okay, it either agrees with what I started with or it doesn't. But with random numbers, you have to check complete distributions, and these distributions are hard to check. So I'll be mostly focusing on the 144 qubit machine in China, and our approach is to verify the moments of the distributions in phase space. And I'll explain how that works. So first of all, what on earth is a boson sampler? In principle, it's a very simple machine. You have some form of photonic network, a linear network. You feed in some inputs, which are non-classical. And then you get a whole bunch of outputs down at the bottom here. And you measure the number of photons that have occurred and work out their correlation functions. And it's known that, for example, the correlation function of the number state outputs, if you multiply all of these operators together and you've got either 0 or 1 photon inputs, then the result is a matrix permanent. The matrix permanent is an exponentially hard function to evaluate. You just can't evaluate matrix permanence more than about 50 by 50, even using the biggest supercomputers in the world. And it's even harder to sample a matrix permanent if it has this distribution. So that's the classic problem, but number states are hard to generate, so people switch to squeeze states. In the case of squeeze states, the expected output distributions are not permanents, but they're Torontonians, which is a strange function invented by some people in Toronto, or Hafnians, which is another well-known matrix function. Now, you might expect the output distribution to have a certain form, and the experimentalists always assume that it does, but you have to ask, what distribution does it actually have? How can you prove it's a Torontonian or a Hafnian? Now, other methods of analyzing this have only treated low order correlations. We have a technique that can analyze all orders of correlations and bin them so that they're actually measurable. Okay, so first of all, let's just talk about how this computer works. So I'll just go back and remind you, we're going to put some inputs into a photonic network and get some outputs out. Okay, so what are the inputs? For the Gaussian boson sampler, they just use multimode squeeze states, which is a well-known technology since the 1980s. You generate them using parametric down conversion. And you have a vacuum that's produced, which has got more vacuum fluctuations in one quadrature than it has in another quadrature. So it's non-classical. The actual definition is this exponential of quadratic form in annihilation and creation operators. And in the experiment, you have some output modes, and they would be given in an ideal case by a unitary transformation of the input mode operators. But because of losses, you have a transmission matrix and some reservoir terms as well. So that's what actually happens in a real experiment, but it's still a pretty simple setup and quite straightforward to analyze theoretically, or so you would think. Okay, and you can do it in the lab. This is the USTC China experiment, their largest one. It has 144 superconducting edge detectors. And as you can see, it's a reasonably complex system, but it does work, and it has been demonstrated to operate in the lab. Now, for these superconducting edge detectors that they use, the outputs are either 0 or 1. So how do you represent zeros and ones as an operator in quantum mechanics? Well, the photon number operator, I'll call n prime. This is just A dagger A of the output fields. And for clicks, the expectation value of a product of these clicks is the product of these projectors pi j, and the pi j projector is known to have a normally ordered form as e to the minus n times e to the n minus 1 to the power c, where c is the number that tells you whether you have a vacuum or a photon. So for no photons, Cj would be 0. For one or more photons, Cj is 1. And this Torrentonian is what you would imagine you could use to check the outputs. I mean, you work it out, whatever it is, and then you compare it with what you measure experimentally. Seems very straightforward. Unfortunately, it doesn't work. So, and I'll explain why in a minute. But that's not the only technology. And there's also some more sophisticated photonic technologies. Here's a programmable photonic chip. And this is a device that's used in the more recent machine that's been published, whose results are published by a collaboration between NIST in the US and Xanadu in Canada. They call it the Borealis. It has 216 photon number resolving detectors. This is not a picture of the machine. I haven't been able to find any photographs of the actual machine in operation. I suspect it's considered to be commercial in confidence because they have a corporate partner. What they measure is the actual output number distribution. And it turns out that's described by a matrix function called the Hafnian, which is the mean value of this product of projectors. Well, they're not actually projectors, but they're projection-like quantities, where PJM is 1 over m factorial times another normally ordered product. But in here, MJ can be 0 for no photons, but for more than one photon, it's a resolvable number that can be 1, 2, 3, or 4 up to some limit. Now, let's talk now about the theory problems. First of all, generating samples from the Torrentonian or Hafnian is known to be, from the computer science perspective, what's called a hash-p-hard problem. It's exponentially difficult to do this. Every sample is exponentially hard to generate. There are a number of classical samplers proposed to do this, and they can work up to about 50 qubits at the moment, using the world's largest supercomputers. But after this, they take exponentially long times to operate. It doesn't scale linearly. And for current size devices, you would need billions of years to produce the outputs, just even one output. Now, a GBS device makes one sample in around about 1 nanosecond. So that's the computational advantage people are talking about. You can make a sample classically in billions of years, or you can do it on a quantum device in about a nanosecond. That seems like a big improvement, although it is slightly problematic since it only solves one problem, which is how to generate these particular random numbers. Okay, so next, why is it tough to compute the probabilities? Well, it turns out that it's not just hard to sample, but even to calculate the values of the Torrentonians or Hafnians is also hash-p hard. Every output is exponentially hard to compute. In fact, it's really hard to compute even one probability, just like it's very hard to generate even one sample. But there are about 10 to the 43 possible outputs. So to get all the probabilities, well, you need to compute and store 10 to the 43 outputs. So let's suppose a miracle occurred and you could compute one sample per nanosecond. Well, you'd still need 10 to the 18 billion years to actually finish the job of working out what all the probabilities were. And 10 to the 18 billion years is a long time. Now, what is not often mentioned is that many of these issues also occur with experiment as well. You can generate a sample quickly, but if you want to estimate the value of the whole Torrentonian, you would need one sample for every possible bit pattern C. or at least one sample, preferably more than one sample. Now, typically experimentalists generate between 10 to the 7 and 10 to the 9 samples when they run their experiments. But the individual probability of any one particular pattern of ons and offs, well, that's of order 10 to the minus 43. So even sampling 1 per nanosecond, you need 10 to the 18 billion years before any particular output is likely to occur. Again, that's a very long time. And this is the experimental time I'm talking about now. And you do need at least one output to estimate a probability, and preferably 10 or more. So the truth is, you can't even measure these probabilities experimentally, even though you can generate the samples. Okay, so how are you going to verify this? Now, the only sensible way to do this appears to be some form of grouped or binned count probabilities. So we can define the most general binning technique as an nth order grouped probability, which is defined as the expectation value of some binned combination of these projection operators. So what does this mean physically? It means you're going to divide up all of the detectors, for example, into 2 halves, and then you'll get the probability that, say, the first half gives you a total of 10 counts, and the second half gives you, say, a total of 30 counts. And that would give you a 2-dimensional probability distribution, and it's a much smaller dimensional probability space than before, and you can actually measure that experimentally, and you can also compute it if you have the right techniques. So it is these quantities here, these grouped probabilities, that we're going to use to diagnose and check and verify that the quantum computers are working. And there are similar methods for photon number binning for the NIST Xanadu computer as well. Now, although you'd like to use some well-known traditional method, it turns out that you can't really simulate this with any of the usual textbook methods. The Hilbert space itself has exponentially many dimensions. There are no computers big or fast enough to use number states to work those things out. Glauber's P function is quite a popular phase-based method, but it's singular for squeeze states, so you can't use it. It just doesn't give a probability, and you can't sample it. Wigner functions actually are positive, so they could be used in principle, but when you try to use them, they have exponentially large sampling errors, so they're not very useful either. In summary, traditional theoretical methods do not work. But you can simulate these grouped probabilities with positive P representation. And the reason why you can do this is because the positive P method is normally ordered, so it doesn't have a large amount of vacuum fluctuations in it, but it also allows non-classical sampling with probabilities. And that's a huge advantage because you do need to sample when you have systems of this scale where things can't be treated deterministically. Now, the first question, which you have to consider here, is really interesting. You might think, oh, well, if you can simulate the machine using positive P, then you don't have any quantum advantage anymore. So what was the point? You might as well just close the whole thing down. Now, that's not true. The positive P method generates real continuous numbers with some distribution. It happens that from these real continuous numbers, you can generate all of the discrete probabilities of bits that are needed to verify a GBS machine. But the method does not generate the random bits directly. And we don't know any way of kind of unscrambling this. We don't know any way of taking the positive P method and going back to the random bits that might have generated that. Maybe somebody would invent that in future, in which case that would be a disproof of quantum advantage, but no one has done that. So it's not a replacement for the GBS machine. However, it can be used for verification. We can use this to determine if the answers are correct or false. So now we can ask the question, does the machine give the expected answers? Okay, so to answer this, you first have to run your simulation, and that's pretty straightforward. It turns out that the stochastic model for the input squeeze states are just Gaussian random numbers, which you can generate very easily on a computer and very efficiently, although admittedly they are pseudo-random numbers. They involve these numbers delta, which are interesting. If you have a pure squeeze state, then these deltas are real. If you have a sufficiently thermalized squeeze state, then the deltas change from real to imaginary, and you get a Glauber-Sudershan p-representation instead, which you could actually use to generate random numbers and use that to fake the quantum computer. But we're going to start by considering a case when we have got squeeze state inputs. Next, you have a transmission matrix, which is typically around 10,000 numbers. And using that transmission matrix to do a calculation for number states would be exponentially complex. And these exponentially complex methods, they tend to fail above about 50 modes. But the big advantage of the phase-space methods is that you only have to do a simple matrix multiplication, an m by m multiplication in polynomial time to take care of the transmission matrix. You just take alpha prime as T alpha and beta prime as T star beta. And this approach has already been demonstrated to scale up to 16,000 modes, much bigger than any of the experiments. So clearly it's a very scalable approach. But that's not the hard part. The hard part is the binning, because as I said, you have to bin many results together. Otherwise you won't have anything that'll have a large enough probability to measure. But it turns out there's a very nice little piece of algebra you can use to do this. You use a discrete Fourier transform. You work out the expectation value of a quantity I call G tilde K, which is a Fourier transformed version of the normal click projection operator. It's a vacuum projector plus a single photon projector with a phase factor. That you can work out very easily using these phase-space methods. Then you apply an inverse Fourier transform and get the actual results that you need to obtain for your comparison with experiment. The inverse Fourier transform is polynomial. That means you can do it. Nothing that's exponential is doable in these sorts of calculations. They just take too long. Anything polynomial or involving logs, you can do, at least as long as the numbers don't get too big. So this is perfectly a reasonable thing to calculate. So here's some results where we see the predictions for the total number of output counts for squeeze state inputs for starting from 16th order correlations up to 16,000th order correlations. And you see this characteristic narrowing of the distribution function as the number of photons involved and the number of modes involved increases. But clearly, there's no problem in trying to simulate the present machines, which are around about this green line here. And if they make them bigger, we can always go larger and larger. It's not a difficult thing to do at all. But the first thing that we do when we make these comparisons is we notice huge mismatches, because these are extremely accurate simulations. We can do simulations much more accurate than the experimental data is. And when we compare the probabilities very carefully, we find typically 100 standard deviations or more mismatches if we generate the data using the measured values of squeezing and transmission. Now, Next, we assume that there are some systematic errors in their calibrations. Not a big systematic error, by the way, only a few percent. And we find that typically if we replace the inputs with slightly lower coherence and also modify the transmission slightly as well. And by the way, this is still a GBS machine of a different type. It just has different parameters that describe it. We get much better agreement between theory and experiment. Now, here's a typical kind of result that we would get. This is the comparison of output to input, simulation versus experiment. These are for single photon outputs, single channel mean outputs, which vary all over the place due to interference effects. And the blue and red lines are really tracking each other very accurately, but it's not accurate enough. They have significant differences when we compare them with the expected sampling error from the experiment. So, in fact, experiment and theory don't agree. And this pattern continues for second order correlations. We get a similar thing with even larger discrepancies. For total counts, we get discrepancies. Again, here's the discrepancy here where we subtract the theory from the experiment and just see how big the differences are. So what sort of discrepancies are we talking about? Well, in this case, this is a very high order correlation function. Now, we only have 84 valid bins in this particular data set because some of the bins just don't have any occupancy. We have to discard anything below 10 counts for statistical reasons. We find the ratio of the chi-squared value, that is the Pearson chi-squared test, divided by the number of valid bins is 11. It should be 1. So we're 10 standard deviations away from having the correct outputs in this case. But the reason why this is not such a big discrepancy as before, at least apparently, is because the sampling errors are starting to grow. And they grow even more if we go to multidimensional binned outputs, like dividing up the output photodetectors into 2 halves. In that case, for example, we get 1,500 valid bins here, and the discrepancy goes up to a factor of 33 standard deviations. If I do a 4-dimensional binning, which you can do, you've now got 100,000 different measurements that you're computing, but the number of counts in each bin is very small. So as a result, the experimental errors get bigger and bigger. So eventually, it seems as though things are agreeing better, but in fact, it's slightly misleading because you can't measure the experimental probabilities very accurately anymore. Okay, so in summary, in the recent boson sampling experiment Gzang 2, which is claimed to have a quantum advantage with up to 144 qubits, the counts do not appear to have the correct distribution. The results look fine if you just eyeball them, but when you test them quantitatively, you find they fail. And it's worth adding to this that testing random outputs of computers of various types is quite a well-developed field in statistics. And the tests we're doing are the ones you would normally apply to any random number generator. Like, for example, just generating uniform random numbers. And normally all chi-squared tests get passed. Normally the chi-squareds over k ratios are always of order 1. You don't get discrepancies like 100 standard deviations in normal random number outputs. So we have to conclude that it's fast but not accurate. And that's okay. I mean, these are the first experiments. Maybe they just need to be improved. But at least we can use this information to try to work out what might be causing these problems. Now, let's go through some possible physical explanations. the first one that comes to mind is nonlinear effects. But this does not seem a very likely explanation when you check it, because the number of photons is such that nonlinear effects are very small. There seems to be no possibility of enough phase shifts occurring from nonlinearities in these experiments. Okay, another possibility is maybe it's because it's a macroscopic version of quantum mechanics that you're using with very large Hilbert spaces. Maybe quantum mechanics fails when you get to large Hilbert spaces. And that has, of course, been suggested in various scenarios. I'll just put the word unlikely here. I don't think that's a likely explanation, because these sorts of photonic devices, they have been tested in other situations with even more photons, and we haven't seen any obvious failures of quantum mechanics occurring at all. What we have noticed, though, is that when you optimize parameter values, it seems to help a lot, which seems to be the case that the input parameters may not be measured correctly. And this does create a problem for a computer, because you shouldn't have to go back and change the problem after seeing the solution to the problem from the computer. You should be able to set the problem up and then solve it without having to go back and saying, well, actually, it was solving a different problem. Now, most likely what's going on is that in addition to problems of parameters, the system is fluctuating in time. And we have some evidence already to indicate that there could be some classical noise in the system, maybe in both the squeezing parameters and the transmission parameters. So it's generating outputs, but the outputs are coming from a different type of quantum computer every time they generate a new sample, which obviously is a problem. Now, the big question at this point, which is being debated in the literature, is, does this destroy the quantum advantage? And it is known that a noisy Gaussian boson sampler would be easier to fake classically. If they're sufficiently noisy, they start to behave classically. Now, we have been using randomized sets of binnings, which you have an exponentially large number of possible ways of doing the tests. And these appear to be very difficult to classically fake. Even though it might be easier, it's not clear that it's possible. Some of the first published data from Gzang 1, which is the 100-qubit machine, does appear fakeable. And there has been a proposal from the Xanadu theorists that the Gzang data is fakeable. But they have not been able to fake Gzang 2 data, and nor have we. So the question is perhaps currently an open question in computer science. We know that an ideal GBS can't be faked, but how noisy does it have to be before you've got something that really isn't particularly useful as a demonstration of quantum advantage? This is an open question, I would say. Okay, now looking out to the future a little bit, we know that the p-representations scale well for linear networks, and they work extremely well for the Gzang type experiments using GBS. But this representation is not unique, and we know that for high nonlinearities, you get sampling errors that grow in time if dissipation is low. So it's not an ideal method for future nonlinear low dissipation networks. For example, superconducting networks with Josephson devices, which are kind of the standard now for superconducting quantum computers. And probably also other kinds of devices will be constructed with this kind of technology in future. Perhaps the icing machine, which NTT has proposed, which has many useful applications, may take this path in future. But how would you then check that these things are working? And how would you design them? So what we are proposing for this kind of environment, in work I've been carrying out with Professor Margaret Reid, is using the Q function technique, which is a different phase-space representation. It's scalable, but it's unique. So the growth in time you get in the P function case would not occur. The problem is you have to find some way of constructing phase space trajectories in order to do a simulation. So we have to look at how you do a quantum simulation using this method. Now, with the Q function, in fact, like the P function has a similar property, you use operatic correspondences to make a Fokker-Planck equation, which you then simulate. Now, the problem is that the Fokker-Planck equation for the Q function looks like a Fokker-Planck equation. It has this standard form, but this diffusion matrix, D, is no longer positive definite. In fact, it has a trace of 0. So this effectively corresponds to simultaneous positive and negative time evolution. It turns out there's a real action principle involved, but it's not the Feynman action principle. You have to impose boundary conditions on this in the past and in the future. So it's a little bit like an S-matrix approach in phase space, where you're working out transition probabilities from one state to a different state. The actual equations you get with this approach are called forward-backward stochastic equations. They're stochastic equations where you have one equation that starts in the past and propagates forward in time, another equation that starts in the future and propagates backwards in time, and they're coupled together. And this creates things known as cyclic causal loops, where things can affect each other in both time directions simultaneously, which is very interesting philosophically, but mathematically it's a little bit more challenging to solve such equations. So it's not actually a new type of equation in mathematics. Similar problems have been known to occur in stochastic control theory and in financial mathematics, but solving them is interesting, and it's a nice problem in theoretical physics to work out how to solve these things. But we believe this is a viable future path for such verification problems, because there is no exponentially large Hilbert space involved. Although I must admit, we've only solved these equations in simple cases so far. There is a Lagrangian for this kind of equation. It has an action principle, as I said. The Lagrangian is not the classical Lagrangian, nor is it the Dirac or Feynman Lagrangians. It's a new type of Lagrangian. But it's quite a simple Lagrangian, just a quadratic in the time derivatives, as you can see. So in some sense, it's similar to the classical Lagrangians that are used by Dirac and Feynman, but it has different terms in here. They're not the same terms you would get in those standard Lagrangians in the textbook. You have interesting things as far as stochastic equations occur. You've got fixed past and open future boundary conditions in the action principle. So you start a trajectory for the future time propagating variables at some definite point x0, but in the future you can only constrain the derivative. For the negative time fields, the reverse happens. You can constrain the future position y, but at the present time you can only constrain the time derivative y dot. So what this looks like, if you want to make a little picture of it, is that unlike the positive p, which propagates stochastically in one time direction, we've now got something propagating stochastically in two time directions at once, with couplings between the forward and backward time terms. And these interactions lead to interesting correlations. And it's worthwhile adding that the idea of having such future boundary conditions in physics is actually not a new idea. In fact, these have cropped up time and time again in physics, usually in classical physics, but also in quantum physics. So they've been proposed initially by Schwarzschild who invented the solution to the original black hole problem. So not a bad theoretician, I would say. Dirac, another reasonably well-known theoretician, I feel. Wheeler, Feynman, also David Pegg up in Queensland proposed such similar things. And recently Ken Wharton in California has been also pushing these ideas. So future time boundaries are not that new in physics, and they do have very interesting problems when you combine them with stochastics, as we're doing. And in fact, we've already made some progress. So for example, squeezing Hamiltonian would be a simple example of how to do this. And there's the original Hamiltonian. This is just a single mode system, but the methods work in with many modes as well. And by introducing quadratures, you can find a Q function equation, which has one positive diffusion term and one negative diffusion term. And this is equivalent to a forward-backward stochastic equation. This one you can solve quite easily. We have solved it and then compared it with the quantum solutions that you expect, and they agree exactly. So this, at least in this simple case, this approach works perfectly well. And it does appear to provide a possible route to simulating more nonlinear quantum devices that are currently being developed, as we go past the GBS stage. And of course, observables can be calculated just by doing stochastic averages, as you do for the positive P. So this is very straightforward as well. The main problem is that if these two drift terms are coupled to each other, you get cyclic causal loops, and this makes these equations harder to solve. So, in summary, phase-based methods appear to be very useful for treating quantum networks and potentially for other kinds of quantum computers as well. And in a sense, this is simply a very well-controlled corner of what happens for large quantum systems in the universe. So it's a good training ground for any technique that you want to test out. We've shown these methods work extremely well for the coherent Ising machine, and that they can be used to accurately simulate boson sampling. They are around about 1 billion times faster than competing methods at present. We've carried out the first large-scale high-order test for GBS, and unfortunately, the GBS results were very close to being correct, but they're significantly different from what they should be theoretically. In future, we expect to extend these to quantum nonlinear regimes, and the idea will be to go from the P function to Q functions with these forward-backward equations. And finally, here are some recent publications. If anybody's interested in following this stuff in the literature, there's quite a few papers published in 2022 and some more publications that have just come out on the archive in 2023. So thanks very much for your attention.
Well, thanks, Peter. That's really, really interesting. Lovely to see the old Feynman-Wheeler retrocausality thing coming back in. I always thought that was a lovely idea.
Indeed, very lovely.
And of course, there have subsequently been, an attempts to build interpretations of quantum mechanics based on that idea as well, haven't there?
There have been, and my colleague, Professor Reid, is heavily involved in that.
Ah, that's fascinating stuff. Yeah. So if anyone have any questions, please feel free to type them in the Q&A. We can also, if you type them in chat, I'm sure we can navigate there as well. So I'll just ask a few questions to get the ball rolling, maybe. So being totally naive in this stuff, the Torotonians and the Hafnians, they're basically just relatively simple measures on matrices. Is that correct?
Yes.
I saw one.
Yeah, you
equation, I think.
you can write an analytic formula down, and
yeah.
I didn't bother to do that, but you can, you can write the formula down.
Okay, and the Torotonian has nothing to do with the old what was it called? The old Toronto function, which was a much more complicated thing, involving gamma matrices and hypergeometric functions. It has nothing to do with that, obviously. It must be unrelated to that, I think.
I'm not familiar with the old Toronto.
Yeah, no,
so I'd have to check
it
that
goes
before
back. It goes
maybe
back.
there is a relationship. I'm not sure.
Yeah, well, maybe there is. Okay, so on you mentioned what did I say? So yeah, on your slide 35, you mentioned yeah. So the problem you mentioned, there was a problem for nonlinear low dissipation networks.
Yeah.
Is that problem coming in because of the positive P representation?
It is.
Yeah. Okay. All right. Okay. So it's related to that.
The positive P uses a particular trick to represent quantum mechanical states, and one of the sort of advantages or drawbacks, depends how you look at it, is that it's not unique. So the lack of uniqueness is kind of good because it allows you to choose an appropriate representation that suits a given state. But it turns out that dynamically, it almost always leads to phase space distributions that have tails that grow out in time. So the distributions become less compact in phase space.
Right.
And they sort of go from one non-unique to a different non-unique representation when there's nonlinearities. This doesn't occur for linear cases.
Right.
Now, if you have dissipation, as you do in most experiments up to recently, it turns out the dissipation controls this. But if dissipation is very, very low, you get increased sampling errors due to this non-uniqueness. And that's a significant problem.
And then what happens in the non-small noise limit, if you like, to the positive P representation and to the viability of using that for this? Is that a particular problem?
The noise is not a problem. I mean,
noise is not a problem.
All of these calculations are done right now with, very large amounts of quantum noise, and that doesn't cause any problems.
Oh, right.
It's when you have large nonlinearities, and for the photonic devices, that's not likely to be a problem. You can work out how big nonlinearities are for typical photonic devices, and even if they increase nonlinearity enormously, it still would be quite fine. But for superconducting networks, they're really nonlinear.
Yes, extremely, yeah.
That's right. And so if people go down this path, which I think is quite likely, we'll need something new.
Right. Okay. Yeah, I was going to ask you about Q representations, and then you mentioned it. What about something like Wegener representations? Is there any potential there as a means of solving the problem?
Actually, no.
Okay, right.
We've certainly investigated that.
Right.
So in principle, the Wegener representation could be used for GBS because it also scales well, but it has exponentially more sampling error than positive P.
Oh, I see.
So you just can't get useful results out of it.
Well, that's...
and when you go to nonlinear systems, it has third order terms which have no stochastic representation at all. So it's almost useless for this kind of problem.
And arguably, perhaps it's even more sensitive to noise. It doesn't have the noise immunity that you were about in relation to positive P, or was that not true?
It's a different mapping, and it has different properties. It's very useful for calculations on many problems in physics, but not for this one.
Do you see any future for things like, I don't know how you do it, this is just an off the cuff question, but do you see any potential for quantum annealing type devices to solving these Gaussian sampling problems?
You're probably thinking about the Canadian company.
Yeah, exactly. Yeah, I was thinking
D-Wave.
Yes.
Yeah. Okay. So D-Wave is a competitor with the icing machine, and they solve problems that are different. They're solving problems that are actually very important problems in industry, and medicine and many other areas involving optimization, like the traveling salesman problem and similar problems.
Yeah. And
But
I think I think for ground state calculations to spin glasses and things like that.
Yeah,
any system where you've got lots of local minima and you want to find the global minima, I think is probably amenable to that.
I honestly haven't heard of any way of mapping between this hash P hard problem you get in GBS with the traveling salesman problem.
Right. Okay.
They seem to be a different class of hard problems.
Yeah, different class of hard problems. There's 4 questions in the Q&A panel. Let's go. Murdoch Brewer, I hope I pronounced your name correctly. Could you please clarify what is a backwards stochastic equation? Fascinating. It's a fascinating topic. I'm not surprised that it inspired questions.
Okay, that's fair enough. But this is the definition of the kind of forward-backward equation I'm talking about. This is an conventional stochastic equation on the top, where x starts off with some initial condition at t0, and you add noise and drift to it, and you continually change x in time, but going in the forward time direction, starting from an initial condition. You can also have a stochastic equation that has a final condition. So here, when t is tf, you have a well-defined value. Y of tf is given by this boundary condition. And these intervals are all integrated from t up to tf, not from t0 to t. So this means this second term here starts at a future time and stochastically propagates backward in time, getting increasingly noisy as you go backwards in time. And when these two are coupled together, then you get really interesting things happen. Or actually challenging things, I would say, too. These equations, by the way, you'll find slightly modified versions of these equations used in the financial literature. They're considered to be quite useful for describing certain financial problems, maybe ways of predicting, I don't know, how valuable certain stocks and bonds should be. But I'm not a financial mathematician.
The next question comes from Peter Turner. He writes, I might have missed it, but were photon loss and distinguishability already covered as possible sources for the discrepancy between experiment and theory?
Actually, that's the first part. Yes, we certainly include photon loss, and we've experimented with different amounts of photon loss. Photon distinguishability is kind of interesting, actually. Maybe I'll just go back a little bit and talk about that.
Is it not implicit in the statistics of the assumptions?
Let me see. So the photon loss is included in these T matrices, and we've actually tried to optimize that by changing it a little bit. The photon distinguishability, we've assumed that yes, I think there is an effect from that, and we tried to take that into account somewhat heuristically by assuming a reduced coherence. This is known as a thermalized squeeze state. If we assume thermalized squeeze states, then we can improve the results slightly. But this actually could be the reason. It could be that a better and more complete treatment of distinguishability using, for example, different temporal modes or different frequency modes might be needed. At the moment, as I said, we don't have a full physical explanation for this discrepancy and exactly what's causing it. Well, that's still in the future, I think.
Okay, the next question, I've got no chance, I'm sorry. Gopi Krishnan of pronouncing your second name, but I will read the question. How does the complexity of approximating the mode bin distribution scale with the number of bins? Also, the scaling of the number of samples required to validate within some error.
Okay, so if you try to validate within an absolute error, then you can't, it's not a useful criterion. It is talked about, I know, in the literature, but it's not a useful criterion because in terms of validation, we have to deal with two errors. There's error from the experimental data and error from the theoretical simulation. And then we compare them. Now, the only thing that's required in such a comparison for validation purposes is that the theoretical error should be less than the experimental error. And usually it's a lot less than the experimental error. The dominating cause of errors in the data is not the simulation, it's the experimental data. You only have 10 to the 7 data points. And when you have probabilities and you're trying to estimate them from an experiment, it's been well known since the time of Pearson back in the 1890s that everything is determined by the number of experimental samples you have. And essentially 10 to the 7 or so is not enough. That's why you have to bin. And this is always the dominant source of error in these comparisons. So,
and in the experiment, they're using squeeze states,
yes,
yeah,
they're using squeeze states in both these experiments. Yes,
right, okay.
But the output is just some, counts, and they accumulate the counts. Yeah. They get, say, 10 to the 7 of them in one experimental run, and then they put them on a public net, so anybody can download them and analyze them.
Oh, fascinating. And then the final question in the Q&A panel is from Joe Hope, who writes, very interesting, lovely to see phase-based methods do so well on these systems. It seems you have essentially showed that the GBS experiments did not achieve what they claimed, but you also said Zhuzheng 2 could not be faked. Does this mean they got the distributions correct?
No. What it could mean is that they generated slightly different distributions from the ones they claimed, but these modified distributions, which are definitely not what they claim, may still be hard to fake classically.
Okay. And then the next part of Joe's question was calculating the moments is equivalent to calculating the probability distributions. Was this not also known to be hash P?
Yes, Joe, thank you very much for that nice question. Yeah, well, so
wading into the controversial here.
No, it's a fine question. No controversy about that. It's an excellent question. And as I said, thank you very much, Joe. So what's going on here is I don't know, maybe I'll go down to some of the pictures here. It's a little bit hard to explain, but all of the theory that we do has theoretical sampling error in it. Now, because the dominant source of error in the comparisons is experimental sampling error, we're not really concerned about this theoretical computer science point that it's a hash P hard thing to compute. The hash P hardness of it is only really relevant if you wanted to calculate, the entire Torontonian up to some certain level of relative accuracy. Then it's hash P hard. But that is not even you couldn't even store that result, even if you could calculate it, because there's not enough space in the universe to store all that information. I actually mean that literally. There's not enough space in the universe to store all that information. So even though it might be hash P hard, it doesn't matter. It's not a useful thing for doing validation. You have to do this binning, and it turns out by, well, some good fortune that even though the Torontonian's hash P hard, the bin version of it clearly isn't, because we've calculated it. If it was hash P hard, we couldn't calculate it. So since we've done that, we know that the bin version is not hash P hard.
Right. And then the final element of Joe's question, or Joe's statement question, more generally, if there is a genuine quantum supremacy that includes supremacy over even the cleverest phase space methods, does this not guarantee there are elements of these systems that can't even be verified unless it's classically verifiable.
Oh, this sounds like a question for a certain defunct Mr. Goodell. So computation results that can't be verified, that would be a problem, but I don't think we've seen that occurring yet. I guess the one case where it would be a clear problem would be in these optimization problems, where indeed I think it would be valid to say that if you can demonstrate quantum advantage, it would only be some kind of heuristic quantum advantage you could demonstrate. That is, you could prove that you did better than a classical algorithm, but you couldn't prove that you had the best possible answer. So I think if you're interested in undecidable problems, Joe, I think that would be the area to look.
And then he writes, thanks, Peter. And let me add my thanks as well. That was a fantastic talk. Thanks very much, Peter. And I'll remind everybody that the talk will be up on YouTube within a few days once we get a little bit of work done that's involved in doing that. Oh, hang on, there's another question, number 6. Not a question, but still interesting. Michio Kaku is bringing out his new book next month. It's called Quantum Supremacy. Well, there you go. We got a free ad for that.
Mr. Kaku, yeah, okay. I just hope he gives you guys an advertising fee.
All right. Thanks very much, everyone. Thank you very much, Peter. And that was a great talk. And see you all next time. We'll let everyone know when the next talk is happening and what it's about in due course.
Thank you.
Thanks again, Peter. All the best, mate.
Okay.